Okay, I get the problem, I think. Um, Fill each empty room with a distance to its nearest gate. So I don't understand, like, what is a what's the purpose of a? Oh, sorry, there's no guards. For some reason, I thought there was a guard entry. Okay,
There's
yeah,
just
I think I
gates.
understand.
Sure.
Yeah, just okay. So my initial reaction to this is kind of like, let's start with like a simpler problem, which is fill in like one, like a given index, um, with the distance to its closest wall, or sorry, gate rather.
Yep.
And then, we can run that same algorithm basically at every spot and just fill in the array that way, right?
Okay.
So how would you go about finding the minimum distance? I think you can treat this as like a recursive problem, not recursive problem. I think a dynamic program problem, where it's like, so actually, I'm assuming that the moves can only be like left, right, up, down, right?
Yeah.
Right. So, basically, it's going to be the minimum distance between all that it takes to get from your adjacent spots to the nearest gate plus one, right? Because you need to move from that spot to this spot. Does that make sense?
Sure.
Okay, so and then so this is like is that a recursive problem or is that a dynamic program problem? I feel like it's a dynamic programming approach. Originally, like another way you can do it is like a depth first search, which is like you move all ways,
Yeah.
and then you return the minimum of the four paths that you search, right?
Right.
But I think the earlier approach would be faster because that way what we can do is also memorize, store these solutions, and then use them again when you're computing the closest uh, distance from other spots.
So are you just starting from some arbitrary infinity value, or is it something else?
Yeah, so that's what I'm trying to. That's what I'm thinking about right now. So clearly, so the thing I mentioned earlier was, start from the top left. Or a naive way would be to start from the top left and go to the bottom right. But obviously, if you see a wall, there's no way, so you just continue. If you see a gate, the answer is, there's zero. And then every time you see an infinity, then you sort of run this algorithm, right? Um,
Okay.
but
So
but hold on, sorry. It's, I think it would be smarter to start. So, like, if you start at some random infinity, the way I kind of described it is you basically take the minimum of, your four adjacent ones, right? But you can easily imagine a scenario where, you haven't filled in those slots yet. So instead of that, I think a better solution might be to start from a gate, and then for every single valid adjacent um, neighbor, you kind of have a queue maybe, and then you queue them as like you do basically a breadth first search from every single gate. Um, yeah, and then update the value to the depth in the breadth first search. Does that make sense to you?
yeah,
Yeah. So
this follows the thing you'd say for DP, right, where you're using previous solutions.
yeah, 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 um, yeah. So I think that's my general solution. Um, what do you think I can code that up? Sure. Sorry.
Yeah.
Let's analyze runtime complexity, I guess.
Sure. And
It's like,
then after you
yeah.
can code it out.
So for every single node, you're gonna have like four possible children, right? Um, and then I guess the question then becomes, so it's like a 4 to some power, right? And the question is, what's like the maximum depth of this tree? Um, I have a feeling that it's n because that's the length of like a side, perhaps. So I would go ahead and say that this is 4 to the n um, runtime complexity. But
Okay,
that doesn't make
so
sense because we said this is dynamic and it's clearly should be like n squared, right?
I mean, starting off, what's
It's,
the you said you're running BFS, right? What's the complexity for that?
yes, it's,
I definitely don't think that's exponential time, right?
yeah, it doesn't seem like exponential time. I'm really bad at this. You know the general runtime of BFS. So like it's um, you know you visit every single node once, right? Basically, so isn't it like n time?
You mean the number of cells is defined as n?
So sorry, in BFS, given n nodes,
Yep.
it's big O of n. But then in this grid, if you consider n as a length, then there's n squared nodes. So I would say a BFS is a n squared
Right.
runtime.
Sure. Yeah, that
Um,
makes sense to me.
that definitely makes sense to me as well. I'm not sure why I said 4 to the end. That's kind of ridiculous. Okay, so yeah, and then space time complexity or space complexity. Um, we don't need any extra space actually, so it's big O one. Yeah.
So I guess two questions is you
Oh,
said
sorry.
you're
Go ahead.
I think you're no you can go ahead. I think you're about to answer one of them.
Yeah. So I had mentioned that I will need a queue
Yep.
to store like the next neighbors. So then I guess we can go ahead and upper bound that queue with n squared um, space, extra space required. Uh, what's a tighter lower bound though? Upper bound though. Um, yeah, okay. I'll say n squared extra space.
Sure. So the one question that I had is, are you going to be running BFS only once then?
Mm. So I did mention that. Well, actually, yes, I will. And the way it'll end up working. Well, hold on. Sorry. So my original plan was actually to queue all the gates at depth 0
Okay.
at the start, right? Um, and basically, we ignore nodes we've already visited, and we know we visited them because they're not infinity.
Right.
So yes, it's just one BFS.
Okay. Sure. Yeah, that sounds good. And I guess we could cut this out.
Cool. Okay, so let's. What's this problem called? I don't know. Problem. And we're given a board. And is there any other input? I don't think so. Right. So let's go ahead and use collections import DQ. And basically, the way I described it is first you want to queue everything such that you queue every single index of a 0, right? So we want to traverse the board. Board j and range 0 to the length of 0. Basically, okay, and then also, of course, we need to initialize the queue. And if the board at this index is equal to 0, then this is a gate, right? So basically what we want to do is queue.append, and we want to append the index, and we also want to append the depth.
Okay.
Right. Well, now we want to, now I'm just basically going to code up a regular best first search here. So we get the row column, and then we basically, the first thing we want to do is, and this is going to be redundant for the first step, but sorry, no, it's going to be depth plus 1. So maybe it's better to queue it like this. No, I lied. Sorry. Because it just depends on how we queue it afterwards. But anyway,
it seems like it's kind of the same thing, right?
Yeah, it's exactly the same thing. Okay, so we set the board, and then we want to do the queuing. So queue.append row plus 1, column depth plus 1, and I'm just going to copy and paste this 4 times. And obviously we need to worry about bounds as well, so I'll handle that next.
Sure.
Sorry, this is not right. Rows, go up 1 and down 1. Okay, so basically over here now, so I might be queuing something that is invalid, so we just need to check whether it's valid. So if row is less than 0, or row is greater than or equal to length of board, we just continue. Or the column is less than 0, or the column is greater than length of board at 0. So we can just continue. Okay, so there's actually other situations as well that we need to continue that I mentioned before. The first one being that, this is a wall, right?
Okay.
So, or board at row column is equal to -1. And then the other one, the final one is, sorry, I can drink water. Right. And then the final one that I want to make sure that we're not we're not handling this again is so the two situations are the board is -1, meaning it's an obstacle, or we've already visited it, meaning it's not in infinity, right? So, just for clarity's sake, maybe I'll actually split this into 2 if conditions.
Sure.
So if the board is equal to -1, or the board is equal to infinity, this means that we don't want to that this is sorry, no, does not equal infinity.
Right.
What this means is this is a section that we don't want to do, so we just put a not in front of everything here now, and then we continue. Does that make sense here? So if the board is -1, or it's not infinity, meaning we filled it, then we continue. Yeah, that makes sense to me. Okay, and then
sorry, you can go ahead.
Say again?
You can go ahead.
Okay, so we appended the queues. There's one more problem, which is whether we've already visited. Oh, but no, I already checked that because I do this check here. So the thing I was checking was, normally in a graph search, what you want to do is, there might be back edges, so you have to keep track of a visited set. But that's effectively already done because of this line right here, which checks whether we filled this array in.
Right.
So I think actually this might just terminate. I think this might just be the end of the code, and then we can return board, but
yeah, you can assume that it's in place.
Yeah. So I think this is the full code actually. I guess we can go ahead and try running it on the example you've given here.
Sure, I can help paste that in, just because It is, pretty long, so I can start at the bottom.
Yeah. Okay. Cool. Okay. Is there an extra right back there? Yeah. So the way it works is, the first thing is, you queue the first two zeros with depth of 0. So the first time it'll pop those two, and it'll just fill them with zeros, right?
Okay.
And then we'll be queuing, all four sides, right? So the ones that are out of bounds will be, just thrown away. We're just going to continue from them. That's the case with this. So let's look at this -1 here. So board is equal to -1. So this if statement is true, and then you nod it and it becomes false. Interesting. And then it continues. So I made a mistake here. Do you see the mistake? Do you see why it is a mistake?
Yeah. When you have your not around the condition, it's pretty much the opposite, right?
So if board is equal to -1, or board is equal to doesn't equal to infinity. So yeah, so if board is equal to -1, you want to continue. If the board is not infinity, meaning we filled it in, we want to continue. Yeah, that makes sense. Okay, so we fixed that bug. So now, when it goes to the left, do you see me? Do you see
my? Yeah.
Right, cool.
It shows up.
Yeah, so at this node here now, it correctly just continues, and then over here, what it'll do is because it's inbound, and checking this if statement again, the board is not negative. That index is not -1, and it is infinity. So this whole thing is false. So we go ahead and fill this in with 1 here, and then we queue all the neighbors, right?
Right.
And then it's basically the story for this one here. Let me just line this up. Yeah, and then that's like that depth, right? And then we've queued like everything else, and then for this 0 here, it sees the -1 to the right. It just continues, and then it goes up to this infinity and fills it in with 1, and then it queues the next one with depth 0. Right. Now from this one here, because the top, it'll technically queue the top as well, this 0, which arguably we could check and before we queue, but the code might become messier. But what will happen is, basically this check here will just make it continue, because it's not -1 and it's not infinity,
right?
Not non-infinity. Right. So if we check the right one, continue. The bottom gets set to 2. The left gets set to 2, and then that's the end of that one. And then for this one here, that gets processed next. So for this one, only the top one was a valid path, so it gets set to 2, and then it queues the next one with 3. Over here now, again, based on the same logic, the bottom gets queued and set to 3, and then the top gets queued and set to 3. And then finally, the right here gets set to 4. And I think this is the same board we have up there, is it? 0, 1, 2, 3. Yeah. Okay, so then, I think this is my solution.
Cool. If you want, you can go ahead and actually run code in this. And I'll point out that there is one small mistake, but it's just because of the wording of the problem. The comparison to float is actually this exact number. But yeah, it's the same thing.
Oh, I see. Okay, great. Cool. Okay, I guess we can run the code, like you said then.